All right, well, thank you everybody for coming in. Any questions that you'd like to look at as we begin here?
So, like general questions, I guess you could say.
Okay.
So if a differential equation is in normal form, if f of t of y is discontinuous at a point, is that something that sets our region or where this thing could exist?
Okay, so to repeat the question, if I can, make sure I get it right.
Okay,
If you have an equation in normal form and f is discontinuous,
yes.
how does that affect the region of
Yes.
existence uniqueness? The theorem no longer applies.
No longer applies.
The theorem says this. Given a differential equation in normal form, that's this form, the derivative on the left, for a first order equation, it looks like this. That higher order, you put the highest derivative on the left, everything else on the right. So for a first order equation, this is all we have existence uniqueness there for. In normal form, if you have f and df dy continuous in a big rectangle, then intuitively what it means is the solutions go through every single point. That's the existence part. If you give me an initial value, t equals t0, y equals y0, there's exactly one solution curve through there. So it's a solution curve through every point. That's the existence part. And they don't intersect. If they intersected, right, it wouldn't be unique, right? This initial value would have more than one solution. So existence means there's a curve through every point. Uniqueness means they don't intersect in the rectangle. So they're filling up the rectangle like this. So that only applies when these are both continuous. Well, existence applies when f is continuous. Existence and uniqueness applies if these are both continuous. So if f is discontinuous, you can have the solutions intersecting and have more than one solution, or you can have no solution at that point. The theorem just doesn't apply.
Okay, interesting.
Yeah, so yeah, it only applies if you have these situations.
Okay, so second question.
Yeah.
If the partial derivative is also discontinuous, assuming f is continuous, if it's discontinuous, does that mean that there just isn't a guaranteed unique solution? Or does that mean that there could still be a unique solution, but it's just not guaranteed?
Yeah, I was going to put that in the footnote. So she's saying, suppose f is continuous in the same situation. You have a first order equation in normal form, and this time f is continuous, but the f dy might be the same. If you have an equation in normal form and f is continuous, but partial of f with respect to y is not, then Picard's theorem applies. There exists a solution, but but the Lindelof part that it's unique can fail. There might still be a unique solution, but there are examples where f is continuous and this one is not, where the solution is not unique. And we did one of those last time, actually. That was the square root. If you had f equal square root absolute value of y, for instance, then this is what f looked like. dy plane. And for this example that we did, I like it because it's simple. It illustrates the point. All here and over here, f and df dy are continuous. And so all in the interval here and the interval here, you get a unique solution. But as soon as you get down to here, at this point, it's discontinuous where y is equal to 0. And so if you want the region in the ty plane of solutions, this is the plane for f. In the plane of solutions, so this is just a sketch of f. The plane of solutions, since there's a discontinuity where y equals 0, You have to make a rectangle that excludes the line y equals 0. And as long as you stay in there, you'll have a unique solution. But at this point where f is discontinuous, you'll still have a solution because f is continuous, but it may not be unique. And in that case, we found actually there was an infinite number of solutions. There was y equals a fourth t squared with one solution to our equation. But once it came here, you could continue it down this way with y equals 0 and then break off down here to some other solution. Or here, there's an infinite number of solutions, one that went through this point. Well, I'm sorry I made that too long. If f is continuous, there still exists a solution, but if the f d of y is not, there might be more than one.
Okay, there might be more than one.
Yeah.
Okay. Okay, so
Sorry
then,
to take so long.
that's okay. I have one last question, if you don't mind.
Yeah.
So more of like an example, I guess, because I have to follow up these questions. If you have the differential equation, dy over dt equals negative 2t over the quantity y minus 1 squared.
Okay.
That would be discontinuous at y equals 1, right?
Right.
And so the theorem just doesn't apply.
The theorem doesn't apply at y equals 1, yeah.
Okay,
So here's a good example then. She's asking about the existing uniqueness of solutions to this problem. This is your f of, so we'll say discuss existence and uniqueness. Ever seen this symbol? It means there exists. You put that on there, existence and uniqueness of solutions. To this differential equation. Well, since f, here's actually an important question for the course. Sometimes people are afraid to ask this question because it feels stupid. Don't be afraid to ask stupid questions. I won't grade you on your stupid questions. I'll grade you on what exam scores you got. But where is it continuous is a good question. Because a lot of students feel that way and they think they're supposed to know it from calculus. And you are, but it's normal to not know it. So don't worry. But we have theorems in calculus that basically said all our nice functions are continuous in algebra, right? Algebra being arithmetic, powers, and roots. So all algebraic expressions, I guess I should say, are arithmetic, powers, and roots. They're continuous everywhere except where you get a division by 0 or an even root of a negative number. So for instance, here, this is an algebraic expression, right? It's just arithmetic powers and roots. And so the top one is continuous everywhere, right? There's no even roots of a negative or division by 0. The bottom one also is a algebraic expression without any even roots. There's not even roots at all, right? It's just squared or division by 0. So the top is continuous everywhere. The bottom is continuous everywhere. And then you ask, where is the quotient continuous? Well, the quotient is continuous everywhere except where the denominator is equal to 0. So you say that f is continuous except at where 1 minus y squared equals 0. It's discontinuous because it's not been defined. And so this is equivalently by factoring 1 plus y times 1 minus y equals 0. Or equivalently, y equals plus or minus 1. So these are the points of discontinuity in the ty plane. Now what that means when you go to find a solution to the initial value problem of this together with an initial value, that's what the existence uniqueness theorem is. You have a differential equation in normal form together with an initial value, it determines the solution if f and f dy are continuous. The places where this fails to be continuous in the ty plane are y equals 1 and y equals minus 1. So if you give me any other initial condition, like you give me here, 1, 0, this says that this is the initial condition, y of 1 equals 0. If that was the initial condition, I can tell you there's a unique local solution because of this theorem. Now, why it remains a solution, we don't know. Right? Because it's just no matter how small. But again, as long as it remains in the region between these lines, it will continue to be continuous. It might go down, plot the solutions in another graph. There exists a unique solution through here, no matter how small. I don't know what it looks like, but suppose it looks like this. If it never touches y equals plus or minus 1, then this is the unique solution on the whole interval. So once you find this, you say, oh, that's the unique solution clear through out to infinity and minus infinity. But if it crosses down like this, then the moment it touches the line y equals 1, it could be that the uniqueness fails, right? And or if it touches the line y equals minus 1. So that's the idea of the theorem, is even though it's a no matter how small theorem, you can continue this until it exits this rectangle here. And think of this as an infinitely long rectangle. And as long as the solution you find by separating variables or a linear equation stays between these two lines, it's the unique solution. And then once it touches the end, maybe it's not unique. In fact, it might be that there is no more solution. That's the idea. So it's kind of tricky, isn't it?
A little.
The idea is that this is finding these, this is the uniqueness region, just looking at F, I find these are the two lines and anything that stays between these is this uniqueness theorem applies to any initial condition between these two lines or above them or below them. I could have solutions up here. Then you go through all the solutions over here, the same TY plane, and you think of that region, as soon as it touches the boundaries of that rectangle, then existence uniqueness can fail. Existence if F fails to be continuous, uniqueness if dfdy fails to be continuous.
Cool, thank you.
Yeah. Any other things you want to look at?
I think I have any more questions.
Anybody online have a question? I should make sure this is turned up. Sometimes it's way down.
Look at 4A.
Yeah, out of 2.3, okay. Okay. So here's another question related to that. Just a reminder, we have our first quiz coming up at the end of class on Thursday, 2 days from today. So please make sure you're up on the stuff. It'll be short at the end of class. You can take it in class or online. I'll send it by email if you're online, if you prefer it. So it'll be open book test. So bring all your notes to class or your calculator or whatever you want. That maybe gives you an advantage at home because you get your laptop easier there. But if you bring your laptop here, you can hook into the university system and use your laptop here on it. So bring your laptop if you want. And I might ask you to do these by hand and you can check it with Symbol Lab or something, or I might give you one that existence and uniqueness Symbol Lab can't do, right? But so here's what I could give you is what I was going to say. 4A out of 2.3 is what's been asked for. Solve this nonlinear differential equation by any method. Y dt equals square root y over t, minus square root y over t equals 0. And y of 1 equals 4. Then find the interval of t values, the largest you can on which the unique solution is guaranteed. Then find a singular solution on a larger interval. You picked a hard problem, man. So find the interval guaranteed by the theorem. Unique solution through that point. and a singular solution on a larger interval, like the one we did last time. All right. So what you do is you say this equation is linear. So we can apply either the theorem for nonlinear equations or the theorem for linear equations, but usually the theorem for linear equations is better, it's stronger, right? So if I think of this as, oh, I'm sorry, no, it's not linear. Sorry, it's square root y. Put it almost in linear form. So it's nonlinear. For nonlinear equations, I rewrite them in normal form and use the theorem we just did, the Picard-Lindell law. Maybe I should write that out. It's in the notes, but Picard-Lindell law, something like that. Something like that. I'm not the greatest speller, that's why I didn't teach you English here. So, theorem applies to this, equals square root y over t. This is your f of ty. So you put it in the normal form, the derivative equals the function. And now you say, where is this continuous? Again, it's algebraic expressions. This is continuous. Where in the ty plane? There's a division by 0 at t equals 0, but the continuous except at t equals 0, where the denominator is going to divide by 0, and for y less than or equal to 0. This is kind of a tricky thing in calculus too. You've heard that expression, the devil's in the details, right? I mean, that's true in calculus. Be amazed how detailed it is when you try and get into it. On what interval is f of y equals square root of y versus, this is a separate graph, f of y equals square root y continuous? Oh, it's continuous on the interval from 0 to infinity, right? That's what we say. Well, in calculus, when we say it's continuous on this interval, we don't mean it's continuous on 0, right? Because continuous, you have to be able to approach from both sides. The limit has to exist. Remember the definition of continuity. The limit exists and it's equal to the value, and the function is defined, and the two are equal. So you have to be able to approach it from both sides to say it's continuous at the point. Why do we say it's continuous on this interval if it's not continuous at 0? Because you can't approach it from the left, right? That's the details. The continuity on interval, on a closed interval or half open interval in this case, means that it's continuous at each point on the corresponding open interval, and it's continuous from the right at the left endpoint. And if you have a closed bracket here, it's continuous from the left at the right endpoint. So saying it's continuous on this interval doesn't mean it's continuous at 0. It means it's continuous from 0 to infinity and continuous from the right here. So it's not continuous at 0, even though it's continuous on this interval. That's the tricky stuff in calculus. When you do the theorem, you have to know that difference. So it's not continuous at 0, right? It's continuous on this interval that includes 0, but it's not continuous at 0. So also it's discontinuous for y less than or equal to 0, including it's not continuous at 0. So the theorem says as long as you can make this kind of a rectangle in the ty plane where there's existence and uniqueness of solution. You want t not equal to 0 and y less than, I'm sorry, yeah, t not equal to 0, put it, yeah, and you want y greater than 0. So you cut out t equals 0. That's one boundary of the region. And then you cut out y less than or equal to 0. That's the other side of this line. So what you get is this region is a rectangle on which there exists a unique solution. And also this region, you can pick either one. You can use this rectangle or any subrectangle. Well, why use a subrectangle? It's smaller, right? So where's our initial conditions? It says when t equals 1, y equals 1/4. So go 1/4. we don't need this rectangle. If we had an initial value over here, we could use this rectangle. But our initial condition is right here. So what's gonna happen to our solution is it's gonna remain unique as long as it stays in this infinite rectangle, going out to, in the first quadrant. So quadrant one, anything in quadrant one, the solution while it remains in quadrant one will be unique. So how do we solve this? It's not linear, right? Because it's square root y. So we have to treat it as a separable equation. That's all we have so far, right? So we separate variables. It's dy, we say it's equivalently dy over y, square root y, equals 1 over t dt. So separate variables by dividing by square root y multiplying by dt. Then you can put an integral on it, right? And now the left integral of y to the minus 1/2 is y to the 1/2 over 1/2 or 2 square root y, right? 2 square root y has derivative 1 square root y. Integral of 1 over t is natural log absolute value of t, but we don't need absolute value. Why not?
Because we're only in quadrant one.
We're restricting to this region right here, right? So we'll write ln t and then it's plus c. Who wants to write absolute value when you don't need it? Always putting that absolute value always throws a hitch in the get along. It always makes the problem confusing. All right. Now we try and solve that within that first quadrant. Oh, so this is equivalently then by dividing by 2 and squaring, y equals ln t plus an arbitrary constant over 2 squared. So there, this one we say implicitly gives solution, integrate. Now I'm going to try and solve that for explicit solutions. Curves that satisfy this equation, but are written in the form y equals a function of t. So that's what I'm doing. These are implicit solutions. Any differentiable curve that satisfy this are solutions. Or solutions implicitly given, I prefer to say. Looks like to write it this way. So there are the explicit solutions. Y equals this. And as long as this curve stays in the first quadrant, it'll be unique. So now, where does this exit the quadrant? Well, I need my initial value. All right, apply the initial value. Y of 1 equals 1/4. That says put in 1/4 for y and 1 for t. Ln of 1 plus c over 2 squared. We plug that into the solution set. These are all the solutions. There is one more I should point out. When we separated variables, what did we leave out?
Stationary.
Yeah, a stationary solution. Wherever this one, f of y times g of t has f of y equals 0 is a stationary solution. Well, you put in y equals 0, that's a solution, right? So y equals 0 is also a stationary solution. And these are the integrated solutions. Books don't tend to use that term quite so much as I do, but I like to differentiate them like that. All right, so here's the case. I can't use y equals 0 and plug in this initial value. It doesn't work, right? Y is equal to 0, not 1/4. All right, so the initial value is this one. Makes this true. And now, what's ln of 1? Right, it's 0. It's nothing, right? So yeah. So that one goes away. Now natural log of 1 is 0. And so c over 2 squared is a 4th. That tells me that c must be plus or minus 1. Right? Is the only way I can make c over 2 squared equal a 4th. Well, which one do I need?
Squared.
Yeah, so I have y equals ln p plus 1 over 2 squared if I put c equal 1. or, y equal ln(t) minus 1/2, where if I want c equal, if I take c equal minus 1, this is where it gets tricky, right? There it goes.
So if that's our unique solutions. They have to fit in the region, right?
Yeah, while they stay in the region, the solution is unique, yeah. But there's a unique solution, so I can't have one of them. I think, yeah, let's see. I think these are the same solution. The theorem guarantees it's a unique solution, right? Because f and df dy are both continuous at that point, right? If you take, I forgot to write df dy. Oh, wait a minute. Okay, so this was f of ty. That's definitely continuous in this region here. I didn't finish doing it. And now that says there exists a solution. But df dy is 1/2 y to the minus 1/2 times 1/t. So that's, we haven't talked about how to compute partial derivatives. We better do that today because we're using them. But this is the partial derivative of this with respect to y. And what it means is you just treat, what the partial derivative means is you treat the other variables, whatever there are on there, as though it's c. So you say, what's the derivative of square root y over c? And all the partial derivative is that you take this derivative and say, oh, it's 1/2 y to the minus 1/2 all over c, like that. But then you put back c equals t, and there's nothing more to that, to partial derivatives than that. You just treat the t as though it's c, and then you take the derivative and you put t back for c. So if I say, what's the derivative of this? Oh, it's 1/2 y to the minus 1/2 times 1 over c, right? That's the derivative of this. And you just put in t instead of c. So that's all partial derivatives are. Just treat t as a constant and take the derivative with respect to y. Now this one is discontinuous where y equals 0 and where t equals 0. So it's the same reason we're left with. So it's discontinuous along t equals 0 and y less than or equal to t equals 0 and y less than or equal to 0. So it's the same region. So this is the right rectangle, but I should have written that out before. I got to check both. So let's see what I've got here. Let's see. Yeah, I think these are actually the same solution. Is why it appears to have two solutions. If you try and sketch this thing, this is tricky here, but what does y equals ln(t) look like? Right, this is y equals natural log of t. And then what is 1/2 ln(t)? Let's look at part of this part, right? 1/2 ln(t) is the same function with the y coordinate squished by a half, so it looks like this. Half is tall everywhere. And then if you add a half to that, it moves it up a unit, a half unit, so you've got something that looks like this at intersection of a new point. But if you subtracted half, it moves down a point. If you write ln(t), then it moves down a half unit, you got something like this. But if you square them, they have the same value at t equals 1, I guess, somewhere in here. I've missed something here somewhere.
So I graphed.
Let's, yeah, so let's do this one. Maybe I'll think about that and figure it out later. I don't want to spend too much time on that, but for this solution, it's the unique solution through the point. On what interval is it the unique solution? Well, it's as long as it stays in this rectangle, it's unique. So it's unique while it remains in quadrant 1. Well, that means it's not gonna, since I'm squaring this kind of a function here, right, this one here, it's never gonna touch t equals 0 because the ln(t) goes down to minus infinity, it never reaches t equals 0. It's gonna touch the line y equals 0. So what I do is say it's until y equals 0, which is 0 equals ln(t) plus 1 over 2 squared. Well, the square is 0 and only if the argument is 0, so this means till ln(t) equals minus 1, so you get 0 in here squared, which is t equals e to the minus 1. Right? Take e of each side. E undoes natural log, and you get e to the minus 1. So it's better written as 1 over e, I suppose. So it's unique solution on 1 over e to infinity. Everywhere else, on this interval, you'll stay in the first quadrant, right? T will be positive and y will be positive. So unique solution on the interval from 1 over e out to infinity. That's the t values, t between. Then you can try and construct singular solutions on larger intervals, and I think that's where this one comes in. I need to throw that out, and I'm trying to remember why. Now, when it touches t equals 0, or y equals 0, that's where you have the problem, right? It's where at 1 over e. This problem y prime is equal to the derivative of this. If you think of this as y equals u squared, then the y y equals ln t plus 1 over 2 squared, meaning this is u squared, has derivative with respect to t equal dy du dt by the chain rule. It's 2u du dt, 2u times the derivative ln t over 2. Is 1 over 2t. Where u is ln t plus 1 over 2 squared, so it's ln t plus 1 over 2. So this is ln t plus 1 over 2t. There it is. And it's a t equals 1 over e. So this is at since this is the derivative, at t equals 1 over e, dy dt at the point 1 over e. This means plug in 1 over e. Maybe I should put it the other way just to make it clear. Plug in 1 over e is equal to ln of 1 over e minus 1 over twice 1 over e is what? What's the ln of 1 over e? There's a tricky one. Yeah, it's -1 because you rewrite 1 over e as e to the minus 1. And so this is, and then you pull the exponent down, you say this is minus 1 ln of e. But ln of e is equal to 1, right? Because it's log base e of e, so this is 1. This whole thing comes out to be 0. So the slope is 0. And it intersects that stationary solution y equals 0. So here's a singular solution because it runs into it at that point with the same slope. Singular solution, you can take y equal that function. Y equals natural log of t plus 1 over 2 squared for t greater than or equal to 1 over e. But it's equal to 0 for t less than or equal to less than, well, yeah, let's say greater than and less than or equal. Let's put this on 1 over. That's how it works. And now what you've got is this solution here looks like this. I sort of graphed it over there. When you square it, it doesn't look like that. That's without the square. So it goes off something like that. This one. And then down here, it hits slope at 1 over e. It hits here, and then you can go flat. Like that. All right, and then the other solutions come in. You can make some others too, but here's a singular solution where the integrated solution meets the stationary solution with the same derivative. 0. Both have slope 0. I'm sorry it's been so long enough. Maybe it was too long. I gotta make sure I get on the material there. Is there any questions before I release all that?
Can you hear me, Dr. Stapleton?
Yeah.
Question. Why I missed why did we not include quadrant 2, like where t is negative?
Oh, because the initial value isn't in that quadrant. You can use either rectangle, but you have to use the one that the initial value is in. It has to go through the point 1, 1/4. So you have a unique solution as long as you don't intersect these lines, t equals 0, this line t equals 0 or go below the y equals 0. And so if I have to go through this point, because that's the initial value, I can't ever get over this quadrant without passing out of my rectangle. Had the initial value been y of minus 1 equal to 4, then I would put my initial value here, and this would have been my rectangle. Use the rectangle that includes the initial value.
Okay, thank you.
Yeah. See how good those problems are? I pick good problems in there. They're tricky. You won't get that amount of detail from hardly anybody in this class. We have this listed as a junior level class. A lot of engineers take it as sophomores, and this, when it's listed as a sophomore level class, they don't like you will. But I think it's nice because in mathematical models, you really do need to know, where's the solution, and guarantee it's unique. Well, let's do something that I didn't get to do my wake up call here. I thought while we have this still in mind recently, I ought to do the following video just to get you awake this morning. I didn't know we'd have so many questions, or I would have done this earlier to keep you awake for the questions. Where'd it go? Oh, I know where it went. I moved the page to do the question here, and then I'll have it. We were talking about no air friction on the moon, right? The reason a feather falls slower is not because gravity affects it more, but because of air friction. If you drop an object without air friction, a feather and a cannonball or something, then they'll both fall exactly the same. And here's the ultimate experiment to prove that. This is astronaut Dave Scott from the Apollo missions. I was young at this time. And he's up on the moon. He's got a hammer in this hand and a feather in this hand, and he's going to drop them on the moon. And you watch, they actually fall at the same rate when there's no atmosphere. So let's see if I can get this to work, hopefully. Kind of fun to watch these things, I think. So you can click on this link in your notes and hit the play. All right, so I love that experiment. I think it's a nice illustration. You can see they had fun with it, right?
So I was thinking they brought a hammer, a feather, a golf club, and
Yeah. Yeah, the other one brought the golf club. This guy brought the hammer and the feather, yeah. But we're made a lot of emphasis on going back to the moon in recent years, so this is kind of applicable. All right, on with the new stuff here then. I wanted to do just a little bit more on mathematical models. Let me move this camera back over. You're probably getting bored watching this flip. There we go. That's what I want. Newton's law of cooling. This is another example of a mathematical model, and it's pretty useful. It tells you how if you put an object, if you immerse it in some other fluid, then it has a nice rate of cooling that you can predict. And So in the notes here on page 40, I said, Isaac Newton, he's considered one of the three greatest mathematicians of all time, by the way. Maybe you haven't heard it before. He single-handedly went through a lot of development of the calculus. And people were just amazed at his results. And later Leibniz and the main one figured it out by himself also, was brilliant guy himself. Spoke many languages, just amazing. But Newton, to figure this out by himself was incredible. And amazingly enough, part of the reason he got going was during the plague. They had a pandemic in his day too, right? And while the plague was going on, he sat there and focused on all the studies, and that's when some of his brilliant work came through, was when he was sitting there at home, away from the university, trying to figure this stuff out. So he had a pandemic when he was a student too. And it helped him actually. So maybe he'll come out of this all right. So Newton found that a body pool emerged. Immersed in a fluid, and we'll include air as an approximation of fluid engineers. In a fluid of some temperature T, call it the ambient temperature, the surrounding temperature T0, cooled in proportion to the difference between the temperature of the body so the body temperature, capital T of time little t, that changed at a rate proportional to the difference between the two temperatures. It was amazing he could figure this stuff out. He also was great in optics. I mean, it's just incredible. That's why it's considered one of the three great ones. People always ask what are the other two ones that they usually put in there. It's not necessarily three either. Different books think different. At least him, and Gauss was another one. The great Gauss I told you about already. Probably the last mathematician ever to know all of mathematics of his day. Everybody since then studies little parts of mathematics, right? It's like this branch of topology or this little branch of abstract algebra and number theory or something. That's why I can't do, I can't verify that proof for Mach's last theorem there, is I don't know enough numbers for it. And then Archimedes was the third one. And Euler's pretty much in there too. So I don't know. I like to include him sometimes. I'm technically a 10th generation descendant of Euler, right? His student, his student, his student. I'm 10 students down from Euler. So I like to put him in the group too. All right. So he's, getting PhD and PhD on that. All right. So the change at a rate, proportional means a constant times the difference between the two temperatures. That's right, it is T minus T0. On there I used T hat, didn't I? Maybe I better use T hat. Let's call the ambient temperature T hat. That's the temperature of the fluid or the air. And so if he finds that the rate at which it changes is proportional to the temperature difference, that means you have a differential equation, right? Rate is derivative. The derivative, or rate of change, is a constant times, I put minus a constant, times T minus T hat. Why did I use a negative K? If K is an arbitrary constant. It's because if you have a positive constant here, it makes the temperature increase, right? So right, if T is the temperature of the object, it ought to be cooling down. So you take this positive number, if it's hotter than its environment, and this is positive, you want to multiply it by a negative number in order to make it cool, right? And so the idea is you put negative K, and then you can say K is greater than 0, some constant you don't. It depends on the properties of the thing, right? It'll cool faster in water than in air, for instance. So K depends on what you stick it in. Now, suppose we want to solve this equation, you also need, by the existence of uniqueness theorem, to know the initial temperature. So y of t of some initial time, let's say time 0 just for simplicity, equals T0. That'll be the initial time. What do you think they're thinking? Y of 0, they should have said T of 0. So there's I wrote Y instead of T here by mistake. Typo. All right, so that's the initial value problem where K greater than 0 is a constant. Depends on the properties of what you stick it in. Now, what's the solution to this? How do we solve that? We don't have very many techniques. By the way, next time we're going to start doing a lot of techniques. So don't worry, you'll be. It's just like calculus 2 again, right? Where you could only do a few integrals at first, but then you got a whole bunch of techniques, right? That's what we're going to do. And in fact, solving differential equation is sometimes called integrating the differential equation because that's what it tends to amount to. You got an equation with derivatives, you do an integration somewhere to get the original function back. We're going to integrate the differential equation. We're going to separate variables again, or you can do the linear case. I don't remember which one I did in here. I we should do the linear one. We haven't done that one. Well, I separated variables. It was do it the same as everything else. dt over t minus t hat. Remember, t hat is a constant. I should have put t hat also greater than 0 is a constant. That's the temperature in which you stick the thing. Solve this by separating variables. Divide by t minus t hat, and you get equals minus k. T little t. So I multiply by dt and divide by t minus t hat. Now you can put an integral on each side, right? And on this side, what's this one? Remember how to solve these? You let u equal t minus t hat. And then du is the derivative of that dt, is just 1 dt or dt. So this becomes integral 1 over u du. And it's comes out to be natural log absolute value of u. And again, since this is positive, if we assume that the temperature of the object is hotter, so it's cooling, then we can drop the absolute value and just say it's ln of u or ln of t minus t hat. So that's the integral of the left, is natural log of this. And you check, take the derivative, and you get 1 over t minus t. That's the nice thing. You always check your integral. You take the derivative and get it back. Or you can use your calculator or your online calculator. Now, integral of minus k is minus kt, and then there's an arbitrary concentration. So these are the implicit solutions by separating variables, right? Now we want to see if we can solve those for capital T. And sure we can. We take e to each side, right? Equivalently, this is t minus t hat, a constant, equals e to minus kt plus c. This is little t. You gotta be careful here. That's the time kt plus c. And now, equivalently, it's t equals t hat, the initial temperature, plus. Let's rewrite this. Let's write this as e to the c times e to the minus kt. And we'll call this an arbitrary constant, whatever, c hat or something. Let c hat equal this is now an arbitrary positive constant. C hat arbitrary for a moment. So these are all the solutions to the differential equation. Now you apply the initial condition. T of 0 equals some number t0. So little t and big T are the variables. Everything else, the c hat, the t hat, the t0, they're just constants, right? This is the initial temperature. This one's the arbitrary constant of integration. This one is the ambient temperature you're dropping the object into. You drop a welder or something, you get your horseshoe all hammered out, you drop it into water. T has the temperature of the water, and T is the temperature of the horseshoe. some welder, but somebody works with metals and form. So you apply that, and now you get T zero on the left equals T hat plus C hat e to the zero, right? But that's just one. So apparently C hat is T zero minus T hat. Initial temperature minus the ambient temperature of the water or whatever it is. And therefore the unique solution to the initial value problem I just put in that value for C hat. And I get T equals T hat, the temperature of the water you drop the horseshoe in, plus T zero minus T hat times e to the minus KT, where K is the constant for the particular fluid, the thermal diffusivity constant, I think it's called. There's the solution to the model. What it says, if you think about it from a modeling point of view, is that at time zero, you start at temperature T0, right? That was the initial temperature. And then you add to that the difference between the temperature of the room and the temperature of the water, and the temperature of the horseshoe, times a decaying exponential. So the horseshoe, the hot horseshoe, decays exponentially to this curve T hat, that's the temperature of the water, assuming it doesn't heat up, right? Put it in a big pool or something. So that's what, there's the solution. It decays exponentially to the ambient temperature around it. And that's the solution to Newton's law of cooling. You can predict exactly how the temperature would decay. And you can heat up objects in this way too. And they call it Newton's law of cooling, but you can also heat things up. Any questions on that one? It was just to show you an application stuff to mathematical models, is you can write down an equation, a differential equation together with an initial value and guarantee a unique solution. You can find it. So I gave you a problem. I'll give you a problem on that for homework tonight. They had a much worse plague. People were dying and great numbers now. They didn't have vaccines. All right. I'm going to skip this thing on qualitative analysis for now because that's in the notes. More on mathematical models. I want to get to more solution methods now. I should mention just in passing one last model. This is in there too. This is kind of a fun one. I assigned a problem on it. Sometimes what you'll find on these things is that they're awfully similar. Radioactive decay. How does radioactive decay work? If you have a radioactive substance, it decays into some inert substance like lead or whatever. What happens is some of it's still decay, it's still radioactive, and some of it's not. And so what happens is you can kind of figure out the model. The amount of the rate of decay is proportional to the amount that's left still radioactive. It hasn't decayed into some form. It is proportional to the amount still radioactive. So what you can do is let y of t equal the amount of the radioactive substance at time t. And, here's the model is, y dt is proportional to, means a constant times, the amount present. Well, that's just y. Except, even though this is true, I'm gonna put minus k, so I'll let conveniently k be greater than 0 and it's decay. If I put plus k, if I put a positive number here, well, it says the rate of change is positive, so it's increasing. If the rate is positive, the function increases. So the idea is if I have a positive amount of substance multiplied by a negative number, then it's decaying. The rate of change is negative, right? Negative derivative decays. And then you have to put it together with an initial value, like y of 0 equals some initial amount, y0. So y0 is the initial amount. And there's your mathematical model, right? And you guarantee a unique solution. And guess what? You can solve this one at a glance. Anybody see how to do that one? If you think about it, it's exactly the population model we already did. If we just call this R instead of minus K, it's the population model, right? So it has the same solution, just replace R with minus K. And so we now have a negative constant here instead of a positive one. And instead of exponential growth like the population, you got exponential decay here. So radioactive decay is exponential decay, and it's actually a pretty good model, except that we messed it up when we set off the atomic bomb. You know, all metals since the atomic bomb have a certain amount of radioactivity all over the world. You can tell if they were made before or after the atomic bomb now when you make molten steel. And there's other things that messed it up occasionally, but it's a pretty good model until, was it 1947? Is that when they set it up, I think? So you don't have to do the solution, you already know it. So it's the population model place what was R, the growth rate, by here the decay minus K, where K is the decay rate, and it must be the same solution. Y equals y0 e to the RT, instead of R you put minus K. There it is, immediately. So it's exponential decay. What you have here is P and Y, you start at some initial amount y0 and it decays. And I should point out that an important quantity here, I do this for the science majors because I know a lot of you aren't math majors, is the half-life. They always ask, like, well, how long does it take for it to decay, say, 1 kilogram of uranium to decay to half a kilogram of uranium? You know, it depends on this decay rate, K, which is different for different radioactive substances. Some of them decay over long periods of time, and some over tiny fractions of a second. K to half their amount. So the half-life is the time to reduce from y0 to half its amount, or from any other amount along the way to half its amount. It's always the same. So it's half the current amount, whatever it is. Let's do it at time 0 just to make it easy. What time does it decay to half y0? Well, you just put a half y0 in for y, right? So you put a half y0 equals y0 e to the minus kt. And whatever t comes out to be will be the half-life. So we'll just call it t 1/2 or something. I forget what I call it in the notes. So you just have to solve this equation, and whatever t 1/2 is, that's the half-life. Well, both sides have a y0 in here, so this divide by y0 and you get 1/2 equals e to the minus k times t half-life. And if this number you're solving for, the half-life, is up in the exponential, what do? Yeah, just take the logarithm of both sides, right? The log and then exponential and inverse functions. ln of 1/2 equals ln of e to the minus k times t half-life. ln and E undo each other, and you just get minus K times T half, right? ln of E to the X is X. And over here, ln of 1/2, you can do something with that too. What's another way of writing ln of X? You see this done so much it'd be familiar. ln of 2 to the minus 1, right? And the power rule, ln of X to the P is P ln of X, so this is minus the natural log of 2. So people, instead of writing ln of 1/2, often write minus ln of 2 on the left. Property of logarithms. And then you just divide by minus K, and that comes out right. T is equal to natural log of 2 over K. So whatever the decay rate is, K, if you take the natural log of 2 and divide by that K rate, that tells you how long it takes. I should call this T in half. To decay to half the current amount. So this is a half-life for any radioactive substance is ln2 over K. So if that's Y0, here's Y0 over 2. Right here at T1 half equals 2 divided by the decay rate. Fun. And so it just shows you what you do with mathematical models. And now let's try some more solution methods. And there's a whole bunch of them here. Because there's lots of differential equations, even in first order, that don't fall to being linear or separable, right? Those are probably the most two important methods, so I spent a lot of time on those, even though they're kind of easy. More solution methods. We want to be able to solve other problems, right? Lots more methods. And here's one of them. Do this one next. I'm a little short on time. Maybe I better do I was going to do exact equations first because it's first on the list here. I guess I better do it anyway. That's because there's not anymore. Yep. Just to keep this sort of in order, then let's do exact equations. We'll have to finish this up next time. A differential equation. This time we're going to write it in a different form because it's convenient for doing this method. And what you just have to do is a little algebra to get into this form. Suppose it's of the form m, a function of x and y, times dx, plus n of x and y, times dy, equals 0. Suppose you take dy dx equals f and rewrite it in this form, right? This is convenient for solving equations that happen to be exact. This one is said to be exact, called exact, if m is the partial of some function phi of x and y with respect to x, and n is the partial of the function phi with respect to y. Partial derivatives. Where, remember, partial derivative just means take the ordinary derivative, treating the other variable as a constant. When I write this thing down here, it means put in y equals c, take the derivative, and then put y back for c. That's all it does. Then over here, you take partial with respect to y, you put in c for x, the other variable, take derivative with respect to y, and then put c back for x. That's all it means. So that's the exact equation. In this case, and this has to be the same function phi, right? So same function. In this case, the differential equation becomes, you kind of have to be lucky. This is the method of getting lucky. Really, it becomes, you just replace m by what it is, d phi dx. And you replace n by what it is, d phi dy. And the differential equation is this. And now this next step is calculus 4, which some of you maybe won't see this, but it doesn't really matter because it's just this one step. Those who've had calculus 4, what is this on the left now? It's kind of tricky. I know it's not easy. Remember what this is? If you have phi, a function
The total differential.
Yeah, awesome. For a function of two variables, this is the differential. Just like when you have u, a function of x, you say, what is du? It's du dx dx, right? That's the differential of a function of one variable. If you have phi, a function of two variables, d phi is d phi dx dx, where it's partial derivative. The curly d's mean partial derivative, and the straight d's mean ordinary derivative. So this is a function of one variable, you take the ordinary derivative. Function of more than one variable, you can take partial derivatives. d phi dx dx plus d phi dy dy. Yeah. So what you recognize from calculus 4 is that this is just d phi on the left, and you have d phi equals 0. But now we've got it, we can integrate and get on the left phi, integral of d phi is phi, and on the right, the integral of 0 is a constant. That's just like this is phi of x, y. And so these are the solutions given implicitly again. You have to take pieces of, you have to take curves y as a function of x that satisfy this equation and are differentiable will be the solution. So the solution's implicitly given by this equation. That's all there is to the exact method. Let's see if I have time to do one real quick here. That's too long. Let's just do it. I'll make one up here real quick because my first example is long. This one you could probably solve by one of our other methods already. The idea of this method is when the other two that are easy fail, you go to try something like this. Suppose I said 2xy dx plus x squared dy equals 0. Well, that's my differential equation. This one actually can be rewritten as a linear equation, I think. It might be separable too. But, and in some sense, you know, you can divide through by x immediately and make it easier, but just for a simple example. So now if you write this differential equation, this is n and this is n, what's the solution? Well, if we're lucky, this is the derivative, the partial derivative of some function. So what is m? And the idea is that if we're lucky, then this is the partial derivative with respect to x of some function, and this is the partial derivative with respect to y of the same function. Well, I want to find then what phi is, because the solution is going to be phi equals a constant, right? As soon as you find phi, you're done. It's just phi equals constant gives you the solution. So if d phi dx is equal to this, then what is phi? If this is the partial derivative of phi with respect to x, then phi must be the partial integral of this with respect to x. Right? So I just have to integrate it to undo the derivative. Similarly over here, if this is the partial of phi with respect to y, and we're hoping we're lucky, this works, then the integral of this with respect to y will also give us phi. Why do we need both? Well, you'll see in a second here. Partial derivative, just like the partial integral, just like the partial derivative treats the other variable as a constant, partial integral treats the other variable as a constant. Think of this as c. If I have integral 2xc dx, what's the integral? I pull the 2c out, or the c out, and integral of 2x is x squared, right? Plus an arbitrary constant, let's call this k. So two x k dx is kx squared plus an arbitrary integration constant, c, right? So we just do the same thing with y. Integral of two x y is yx squared. This y replaces k plus an arbitrary integration. But when you're integrating with respect to x, y is a constant, and so any function of y is a constant. So let's call this g of y. The arbitrary integration constant of the partial integration is an arbitrary function of y. And similarly over here, if I do this one, treating x as a constant, well, I'm pulling x squared out, right? This is just x squared integral dy, because you're thinking of this as integral of c squared. The integral is c squared y, right? And then you put x back. Plus some function h of x. Oh, we got lucky. Look, it's the same function within these two things. G of y has to equal h of x. In order for both these to be satisfied, now we see why we need to do both of these. The only thing you can add here is a true constant. This is a function of y only. This is a function of x only, so it can only be a constant c. Therefore, phi of xy is equal to x squared y plus a constant. I'm all done. That's all the solution. So you just find phi by partial integrations, and then you say phi equals a constant is the solution. These are all solutions. I can choose any constant I want. So this is phi. The solutions are now phi equals a constant. Solutions are x squared y equals c. Let's call this c1. And this can be a different constant there, but the solutions are this, like y equals c over x squared is the solution. It's different. It's time to quit. I think I'm over. This will be the last material for the quiz on Thursday. In fact, I won't even do this on the exact equations. Let's see, I gave you one problem out of this section already, but look at 2.4.1. 4, 5, 7, 10 out of the notes. I think I gave you one of those already, right? Was it 7? I think I gave you 7 already. Section, I don't want to do them. That might be what I'm just doing here. Oh, yeah. So that's right. And then look at the text by libel 1.4 number 10. That'll be it then, I think. Yeah. Last problems for the quiz. Thank you for coming in.
Dr. Stapleton,
Yeah.
is there somewhere for the homework problems where we can find the solutions? Because like I've been doing them, but I have no clue if I'm actually getting them right.
Yeah, I don't have answers. I don't have answers, so I have to bring it to class. I'm sorry.
I can check them on like Symbolab or something, right?
Yeah, that's a good idea because they will do some of these. They won't do the existence and uniqueness problems, but it will do some of the solving differential equations, yes.
Okay, sounds good. Thank you.
Uh-huh.